Hi, in today's video we are going to go through this paper named InstructScene, which is used for indoor scene synthesis using the instruction given by the user. So we'll be going through the code base that they have given. We'll be also seeing like how we can train such model and infer it, and also go through the paper InstructScene. So before starting, just to give you a basic introduction about the paper. So this paper is about how we can use text prompts to generate 3D environments, and they particularly have used a dataset. So they have created their own dataset called InstructScene, which we can also find on the Hugging Face dataset. And they use 3 different dataset to create this InstructScene dataset for their use case, which contains the objects, which contains the texture, and also the scene information. So we'll get through it one by one. So let's start with the paper first. So in this, they are saying using natural language instruction, we are able to create indoor scenes. So they have introduced this InstructScene novel generative framework that integrates semantic graph prior and layout decoder to improve controllability and fidelity of the 3D scene synthesis. So there are majorly two parts of this paper. One is the semantic scene graph prior, another is layout decoder, and we'll get to know like what these two parts are about. So this is like the general introduction that they have given, and in this diagram we can see like this is the user instruction: position a gray nightstand to the left of a wooden wardrobe with doors. And also a second instruction: hang a white ceiling lamp with a wooden circle directly above a black double bed. So the system that they have designed, it will be able to create such semantic graph where the nodes will be representing the objects. For example, this gray nightstand would be this brown dot, and the other colors you can see like they have different dots for that. And for every edge, it is defining a relationship. So between this yellow colored node and brown colored node, there is a relationship defined which is front. So in this way, you given a user instruction, we'll be able to generate a semantic graph prior, and using this, we'll be able to generate a 3D scene. So in this paper, they have described such process to do that, which we are going to dive in. And before that, they have also talked about the related work which is done before this paper was out, like graph-driven scene generation, language-driven scene generation, and they have discussed like there were like some problems with all these techniques, and also graph model for generative models for graphs. And they also talked about diffusion model. So diffusion model is generally like used for image-based techniques, like where you first add noise to the network and then you denoise the network to create the final output. Same technique has been used in this paper, but with graphs. And now they are talking about the problem statement here, so we'll go through it once. Denote scene S with S they are denoting like different scenes, the collection of indoor scenes. For each scene has like different number of objects which they are representing by O, and with different attributes C, T, S, R, F. So here C stands for the category of the object. It could be like chair, table, bed. T stands for the location, which is the XYZ coordinate. S stands for the scale or the size of these objects. R stands for the rotation or the orientation, and F stands for the feature vector, which talks about like the feature of the object, and D is the dimension of this feature vector. To set up a scene, one can generate each 3D object and retrieve it from a database C and F. So they are saying like we can already have a library of our own 3D assets which we can then retrieve and put it in the scene, and also maybe we can use a diffusion based technique to create the 3D object itself. They are resized transformed to the scene coordinate by corresponding TS and R. To simplify the process, we opt 3D. Okay, so they are saying they are opting the retrieval method and leaving the generative model of creating those 3D objects for future work. So given an instruction Y, so this is going to be the text prompt. Our goal is to learn the conditional scene distribution Q. So given Y, which is the instruction, we have to generate a scene, which is S. Rather than direct modeling, we employ a well-structured and informative graph to serve as general and semantic latents. Each graph G contains node V. So this is the node and this is the edge. Node V function is a high-level representation of an object, and the edge directly conveys the relation between the objects. So it could be like on top of, on bottom of, on above of. So all these are the relations which are defined by the edge. So they propose generative framework called InstructScene that contains two components. One is the semantic graph prior. Its role is to, given a instruction Y, you have to generate a graph. So that is the role of semantic graph prior that jointly models high-level object and relation distribution condition on Y. And second is the layout decoder. So given a G, which is the semantic graph, we have to generate a scene S that produces precise layout configuration with semantic graph. G is deterministic by corresponding S. The two network yield the instruction driven generative. So they are saying like using these two network, we are able to finally generate a scene, and this is the equation for that. So this is like a combination of semantic graph prior and a layout decoder. So this is the layout decoder, and this is the semantic graph prior. And now they are talking about the semantic graph prior and talking about like how it is working. Spatial relationship are defined based on the distance and relative orientation, such as left, closely, front of, and all that. And in appendix A.1, so they have also defined all the relations, as you can see here. And below is also like a table. So all these are the relationships which they have defined in this paper, left off, right off. And also we can see the rules which are used to define these relations. So for example, there are two objects in the same, we can use these rules to define this relationship. So this is like the position. So here S and O is the subject and the object. So what is the like orientation of two different objects, and D is representing the distance between them. So like in any case, all the objects will fall in these kind of rules, because of which we'll be able to define the relationship. So that is like we basically used to prepare the training data set for the paper. Coming back to the again part where we left off. So problem statement we went through, semantic graph prior. Yeah, we were on this part. So in appendix, like we can see the relationship provided. Layout configuration include T, S, and R. So T stands for location, S is for size, R for orientation. Can be derived from spatial relationship, and we can then leave them to decoder. So layout decoder will be helpful to predict these T, S, and R to actually generate the scene. Here they have given a second diagram. So again, there is like one other model that they have introduced for feature quantization. So semantic feature of 3D objects are extracted from a frozen multimodal aligned point cloud encoder and then quantized by codebook entries. So here we can see there is a RGB point cloud which is already there, and they have the features from the OpenShape model which we already have, and now they are reconstructing the feature vector using their own VQVAE model that they have defined here. We'll also go through it. And on the right side, we have the discrete semantic graph diffusion. So that also we'll go through. So high dimensional features such as with the D equal to 1280. So these are the number of dimension in the open clip, which is already there. But this is like a very big feature vector. So they have introduced their own feature vector model, which is VQVAE. Intuition behind is that there are general intrinsic characteristics shared among the objects, such as color, material, and basic geometric shapes. So they want to encode all this information with the new VQVAE model that they have introduced. And then they have explained all that the loss function that will be used for training this model. So this is basically about extracting the features out of the 3D object. So that is the model for this. Second comes the discrete semantic graph diffusion, which is actually generating the semantic graph for the given an instruction Y, we can generate like a graph. So they have explained it here. It is like a bit tricky to understand, but here what we can see, the graph has these attributes C, F, and E. C is for categories, E is for the relation between which is represented by the edge, and F is the feature vector. Possible to embed discrete variables in continuous space or not in coding. It diminishes the sparsity inherent in the original data and imposes a substantial burden on the network optimization. So they propose this semantic graph prior through discrete diffusion model. So they are combining the graph transformer along with diffusion to create this new discrete semantic graph diffusion, which they have proposed to generate a scene graph. So intermediate, like they have defined the steps, and they have also defined a Q matrix, which is like a transformation matrix to move from one state to another. And they have like described the process of diffusion as well. So in diffusion, like there are two techniques. One is like for adding noise, another is for like denoising to actually generate the final output. So that all they have explained with the different loss function. In diffusion, generally like KL divergence is used as a loss function to check the differences between two distributions, and similarly they have also used it, but independently for C, F, and E, which is the category, feature vector, and the edges, which represent the relationships. Coming back to this diagram, let's try to understand a bit how it is working. Given an instruction, and then like the instruction will be encoded in form of it will be encoded, and then it will be passed to a graph transformer to reconstruct the graph. So that is the actual part. Like given as instruction Y, we have to generate this graph, and above they have explained the training part where they have so this is the original graph, and it is the all mass graph. So all mass graph we can consider at is like a initial noise, and we have to, while denoising, we have to go from this state from GT to G0 where anything is not masked or there's no noise introduced. And also like in the intermediate state we can see like some of the part is masked and other part is not masked. So this is a way like they are adding noise to go from G0 to GT, and then they're denoising to go from GT to G0. So that is the part where diffusion comes in, and graph transformer is like given a text encoder we can generate like some kind of graph output. So that was about the graph diffusion that they have defined. After that comes the layout decoder part. So once we have this graph transformer, which we have seen here, it consists of three parts. One is the edge, node, and the feature vector of the object. Now using this three information, we have to exactly tell how the object can be placed into the scene. So for the output, we would require the TRS. T is for the location, R for rotation, and O for the like which object it is. So T, R, and S for the scale. So if we have all these three things, TRS, we can actually place the object in the scene. Instantiating 3D scenes become easy with semantic graph prior. Denote layout configuration of SI as L. So they have described some terms here. After that, they have also described like the loss function. And we can also see in the diagram. So we'll be going through the diagram 3A to see like how it is being uh, developed. So given a graph, so this is like the graph which was generated by a semantic graph prior. So if we pass through this model, which they termed as layout decoder, we can see they have added this information of TS and R, which stands for location, scale, and rotation. And once we have this, we can generate our scene. In this case, they have used Blender to use this information to put objects inside the scene. In the output scene, you can also see like there are bounding box across each and every object. So internally, it uses like the bounding box information to see where it can fit inside the scene, and we can place them without overlapping. On the right side, we also see the graph transformer model, how it works. So while generating the semantic scene graph prior, you can see like we have given edges as input and V as the nodes which represent every object, and we are able to like form a graph out of it using this graph transformer model. And after that, yeah, they have explained different like experiments that they have done, and also compared it with other models which also do similar job. Okay, we'll skip this part. So ablation studies is there, conclusion, acknowledgement. What else? So they have also given some examples in the bottom side of the paper. Dataset preparation. So they have also explained like the how the dataset was prepared. Spatial relationship extraction. So in the 3D front dataset, we have all the 3D objects. So they have extracted the spatial relationship. View dependent spatial relations are initially extracted from 3D front using predefined rules. So the rules that we have seen on top of, on bottom of. So using that, we have extracted. So given a scene, we can get those relationships. Object captioning. Further enhance the dataset by providing captions to the object. So all the objects which are there, whether it be like a brown chair or a red sofa, all those features can be extracted using Blip. Caption refinement. Once the caption are generated, maybe using Blip, we can use ChatGPT to refine it further and remodel it according to a use case. Instruction generation. Final instruction for the scene are derived from one to randomly like subject object. So this is like the kind of triplets which we obtain for generating the instruction. So it could be like red sofa on top of floor, something like that. Triplets obtained during the first extraction process. Okay. Relation definition. So relation definition we have already went through. So these are the relation, and they are defining it in form of triplets. They have also given like the for refinement what should be done. Descriptions such as color, shape, material are important. Okay, so this is the example. Given a 3D image of brown sofa with 4 legs, multi-set sofa. So given this input, we should be able to get this kind of output, a brown multi-set sofa with wooden legs. So this is like the kind of refinement that they're doing using ChatGPT and generating the instructions. Then comes the model details. They're using 5-layered 8 multi-head transformer, and batch size 128, 500k iterations. So they have also used Blender for rendering the actual scenes which are generated, that we'll be seeing shortly. They have also defined like there are some limitations to this paper that they have proposed. So 3D front contains problematic object arrangement and missing classification even after filtering. Our learned prior may consequently inherit these erroneous cases. Meanwhile, to scale the current 3D scene data set shall run only with 100 of scene in contrast to okay. Yeah, so they have like just tell like what are all the limitations. So one is like if you have so many objects in the text prompt, it won't be able to generate because they are using just a triplet. So if there are only like two objects in the instruction, it would be able to generate the scene efficiently. Okay, so I think, yeah, so these are the examples that we can also see. Add a cornered side table with a round top to the left of the black silver lamp pendant with light. So this is like the kind of output that they are generating. And for the other two, I think, yeah, so this is by artist diffusion. So these are the other two papers which are generating, and this is their proposed method that they have given. So they are just doing a comparison with different examples with the other papers. Okay, so this was a paper. Now let's go through the code which they have given. So in this code, GitHub repository, they have open source their all code, and also they have provided the checkpoints for the model. So first comes the installation part. We just have to git clone cd. Then there's this sh file that we have to run to install all the dependencies and set up the project. We have to also install the Blender. That is simple and straightforward. And then we have to download the dataset in dataset folder. I can also show you which we have done. So this is a dataset folder, and you can see there are two folders inside it: InstructScene and 3D front. So this contains like all the dataset which is required to run this repository. And if we go to this dataset readme file, so this is how the final output of our dataset would look like. So there is 3 different folder which would contain the folders in this way. Another is InstructScene, which would contain this folder structure. And we can use this script to download and set this dataset directory. After setting up the dataset comes the training and the inference part. First of all, we will be training the VQVAE model. So since they have already provided the checkpoint, which we can see on Hugging Face, if we open this, go to files, we can see already there is this path of this checkpoint provided. So we don't need to train it, but still they have provided the code for that. And once the training is done, then we can like do inferencing using this command here. And in this case, I have already done that. So if we go to this output folder, we are going to see 3 folders. So there are 3 models which we are going to train and inference. So if we go to the checkpoint folder, we see there is already this checkpoint. We can like use this checkpoint for the inference purpose. And once the inference is done, we would be seeing this kind of output. One is the eval text, which would be showing like what is the accuracy of the model which was trained. And also we'll be generating some output. And so there are like 4 batches output which we can see here, and this was like the input feature vector, and this is the output. So we can see like both of them are the same images, so it is able to like generate the objects given a feature vector using the model which was trained. So given a text embedding of an object, it is able to actually identify which object the user is talking about, and finally able to use that object. So I can also show you like how we can quickly run this. So if we go back to, so I have created this commands MD files for quickly running it. So for in the scripts folder, you can see like there are different files. So for this VQVAE, there is one training script, other is for inferencing. I'll just run the training part. In training part, we won't be seeing anything because we already have loaded up the checkpoint, but I'll just quickly show you how to run that. So I've already activated my conda environment. So it is saying like source is not there. So we'll quickly add the sourcing. So this, I don't know, like I've seen with other Python files as well. So we just need to add this one directory to the system path to quickly fix that. I'll just copy these lines. Now I'll be able to run that. Now you can see like loading the training objects, and it also loaded up the checkpoint. Since in the so I'll open up the script which it is using. So it is object feature vector sh. So this is the script which it is using, and also you can see there is a YAML file. So this YAML file actually defines like how many number of iteration or epoch we need to run. So in this case it was 2000, and since there is already a checkpoint available for the 2000th iteration, so it is not training it further. So that is why the training didn't happen. But to infer it, we can run the other script, other command which was available. So once the training is done, we have to just run this command. Okay, again the sourcing problem is there. We'll again add that quickly to this file, whatever it is saying. We'll go to this file, we'll paste. Just a second, let me copy that again. So this is the script which is currently running. As you can see, it is doing some evaluation internally, reconstructing the feature vector. So given a text embedding, it is reconstructing the feature vector and getting the objects out of it. And once this is completed, we can see the evaluation output, which is this that I've shown you before. So this is how like you can run this script. Now coming to the other part of the README file. So I'll just open the README file so that we can see what all steps they have mentioned. So the first part was for the VQVAE part, where we have first trained the model and then we have then use the inference part to see the output. Now comes the layout decoder. So layout decoder is a part where if you have already a scene graph available with you, we are able to generate the exact coordinates TRS of the output. So maybe I'll quickly go through this sh file that they have specified. Inside this they have given a script for train SG to SC, where they have explained how this layout decoder was trained. Maybe I'll quickly go through it to understand how it is working. So first of all, it is like loading up all the parameters and everything. I'll close the terminal. So here they are preparing the training dataset. So it is nothing. So the InstructScene dataset, which was already downloaded in the previous steps, they are like loading it up and encoding it. So that's a trained dataset. Again, the validation dataset is also there. Then we have this train data loader and the validation data loader, which they have prepared. After that, they are loading up the model. So if you have already like train the model till some epoch, we'll load that up, and if it is not there, we are going to train it from scratch. But it is loading the model configurations, like the model architecture, which can be used further for training purpose. Okay, coming to the next step. Then they have also introduced the EMA. So what I have read is EMA is used for like smoothing the output. So there is this other model which is also trained parallelly. And this is the part where the training is started. So model.train, they have loaded up the batch, and then we are using this compute loss function to compute the loss between the predicted output and the target output. So that also we can see the compute loss. We are seeing that we have passed a batch and VQVAE model to compute the loss. So if we go inside this compute loss function, we'll get to see that we'll do in some time. And once this loss is calculated, again we are like logging up the stats, and there's also this tensor board functionality where you can observe everything. Yeah, so though that is mostly it about this code of the training. Let's go inside the compute loss function to actually see how this compute loss is working. So in this case of layout decoder, so it is going to be SG to SC diffusion.py, where they have defined the loss function. So here we see XENO. So this sample parameter is the batch which was being passed to the compute loss function. And here XENO, so X is for the objects, E edges, and O is for the object features that we are already getting from the scene graph as the input. Then they have also defined the mask and boxes. So boxes is basically like telling about information about the bounding box. So this is the information that we have loaded up from the patch. And this part, self.network, in which we are passing this XENO, timestamp, and mask, is the part where we are generating the actual prediction. And where are we getting this XENO? If we see, so XENO are directly being provided from the input patch, and this boxes is the output. So we are going to basically compare the boxes output, which is already there in our batch, with the predicted boxes. So here we can see pred and target are being compared using MSE loss. And where is this target coming from? It is coming from noise, and this noise is coming from boxes. So we are generally like comparing this boxes with the network prediction to compute the loss function and then returning it back. So that is the training process for the layout decoder. And now we are going to use the inference part to see how we can use this layout decoder to actually generate a scene. So going back to our command section, this is the command using which we can like do the inference for our layout decoder. Let me run this command. So once our training is done for the layout decoder, which is in this case this one, so it is also again going to generate some checkpoints. So this is the checkpoint for the 2000 iteration, and once this iteration is already there, then we can use this checkpoint for generating the final output of our layout decoder. As you can see, it is like generating some scenes and visualizing scenes. Let's go to the part where it is actually using this inference and go through its code, how it is working. Generate sg to sg.py is the file where the inference part of the layout decoder is actually happening. So this is all the parse arguments. We are loading up our raw data set. Train loader, data loader we have defined, okay. EMA. Okay. So yeah, this is the part. So we are like in form of a loop. We are loading up the batches to extract out the information from already existing data set about the object edges, if object like the feature vectors and also the mask. So once we have already trained a semantic graph prior, we'll be getting that data set or that part from the input to the layout decoder from there. But for now, we are just loading it up from our existing data set to evaluate the layout decoder. So once we get this input, after that we are doing like some other operation. So let me see where the actual prediction is happening. Yeah, so this is a part generate sample, which is giving out the predictions out of the layout decoder. So as we can see, object edges and indices, the mask and VQVAE model is being passed to the layout decoder model, and as the output we are giving out box prediction. So box prediction is nothing but the bounding box information of where the object should be placed. So if we like go and see below, we can see out of box spread we are getting some translation, which is the xyz coordinate, size is the scale the in the xyz direction, and angle is the orientation of the object. So all this information we are getting out of the box spread, which is the output of the layout decoder. Once we have this b box params with us with all this information, we can actually place objects within the scene, and they have also explained that how they are doing that. Okay, also on the right side, maybe we can see that the model inference is now completed. Let's quickly check that. First, SG to SC tends to support generated scenes, and we can see like there are different output here. So let's open one and see. So this is the top-down view of the generated scene. So it has automatically like generated the scene given a scene graph from the input data set or the scene graph, and we are able to like generate that out, these scenes out, and this is the evaluation. So there was like 340 incorrect output out of 3848. Yes, so that is mostly it about the layout decoder. So yeah, we were talking about once we have this bounding box information, we are able to actually generate the scenes. That part we are going to see how. So get textured object is the place where we are giving the prediction output to this function get textured objects and getting the try mesh meshes output with bbox meshes and object classes, so that we can use it later to generate Blender scenes. So once we have this try mesh meshes, we are going to, okay, what it is doing. Okay, so this is the evaluation part of the layout decoder, which we can skip. Compare the decoded scene graph with the ground truth. Yeah, that again, evaluation part. Now create a try mesh scene and export it to temporary directory. So what it is doing, it is creating a new temporary directory, and in this export scene function, it is creating some obj files which can be used by the Blender to render the scene. So maybe I can show you that in one of my temporary directory, I had that thing saved. And let me check if it is already there somewhere. I remember I copied it somewhere. Okay, let's leave it. I'll directly go to the temp directory. Where was that output? Okay, so I found the directory where we have the output of the obj file which I'm talking about. So let's go to that. So I think it is inside this folder, generated epoch 9. Yeah, so this is the temp directory which we can see here. So when I was like doing the evaluation part of the semantic scene graph, this template directory I created over there. So we can see like it has some PNG files, it has some material file, and also the OBJ file. We are just loading up these files to generate a scene in Blender. So that is what this part is doing. And once the scene is generating, it is like creating an output and saving it into an image file so that we can easily see that. So this kind of output is generated using Blender. So yeah, this was a part like where we have generated a scene using scene graph, and now we are coming to the third part, which is the most important part of this paper, which is training the semantic scene graph prior, and then also doing an inference out of it. So let's run this command first. So this is just about training the semantic scene graph. And also in the command, you can see we are passing bedroom. So for every command, there's like this room type parameter, and we are doing it for bedroom. But there are like other room types like living room and dining room also available inside the dataset. We can see. bedroom, living room, and dining room that they have created. Okay, I didn't go through the dataset. I'll quickly do that. So InstructScene has these text files for every scene: a dressing chair with a loft bed, desk, and ladder. So all this, it's already there in the InstructScene dataset. And if we open 3 different bedroom, we can see like the train and test different folders for it. And if we open like one of this folder, we can see like there are different files here. Boxes npz is for like the bounding box which is being generated by the layout decoder, but for training that they have created this separate npz file which contains the trs information. Maybe I can show you that quickly. Translations, size, angle, all that is already there in the boxes. Room mask, model, and the obj file, sorry, the npy and pkl file already are there. So this is basically the data set which is there for training purpose and also for validation. So yeah, so again, okay, it is saying the src thing was not found. We'll quickly add that. So once the script is completed, we'll be able to see the output in the out folder, which is like the epochs which this script will be generating. So it is loading up the checkpoint which is already there. Let's open that. SG diffusion checkpoints. You can see like there are different checkpoints, but this was the last checkpoint which it generated. I think I have modified the script before to increase the no, it's fine. Yeah, so already the checkpoint is there, so there is no training which happened, and now we can use our inference script to actually see the output of the inference. So let's go to that command quickly. So this is the command which is used for like the inference part. We'll paste it here and also see if I haven't made any changes to that script particularly. Scripts, inference, SG VQVAE. Yeah, I think the script is fine. We can directly run this for inferencing. So once the inference is done, which we are seeing here, it will generate one evaluation output, which we can see here. So as you can see, the accuracies are all 1, which is like 100% correct. And inside this folder, it is like one sample scene which we have generated using the trained graph diffusion model. And this is a graph output which is internally created for some description like this. Put a gray bed with headboard and pillows to the left of the nightstand. So for this description, our scene graph which we have trained is able to create an output like this. Once the scene graph is created, we give this input to the layout decoder, which can eventually generate scene in Blender that we have already seen. Maybe I'll quickly go through the training script of this semantic graph prior and also the inference part, and that would conclude our session or the recording here. So it is train SG, which stands for training the semantic graph prior. Again, it is loading up the data sets. And here is the part where the model training is starting, and also like we have loaded up the model from our configurations, which is a graph transformer with diffusion. And the main part here is like how the loss is being computed. So model train. Here we can see we have the descriptions which we have loaded up from the dataset, train dataset. And there is this text array which we are creating after using this function fill template. So fill template function is just for if we have like a description which we have seen before in the dataset, which I'll quickly again show you. If we have something like this, it is able to convert the function which we have seen fill template. It is able to convert such description into a text which we require to give as an input to our graph semantic graph prior, and that should be in the form of triplet. For example, bed should go on top of floor. So that kind of change is being done by this fill template function. We can also see how the evaluation of semantic graph prior is done. We will close it. Coming back to the code, once this text is prepared, we then use text encoder to encode that and give it as input to our semantic graph prior model, which we are trying to train. And we can see this compute function where we are like passing up the whole batch, text, last hidden state, and the text embedding. So given our text, we need to actually generate the graph, and that we can see in the compute loss function. So if we open this compute loss function, SG diffusion VQ obj, this is the compute function that we are looking for. Unpack the sample parameter. So from the batch that we have loaded up, so this is the input, which we are giving to the model that we are going to train, XEO. Sorry, input is a text embedding. I think this XENO is for like for comparing the output or like computing the loss. But where is the model prediction happening? Let's see. So yeah, train loss is a function where we are like calculating the loss. Let's open it up. So we see like there's a long code which is there for calculating the loss, but internally it is all talking about how diffusion is working with the graph transform model here. And below we can also see we are using some KL divergence loss to see the difference between different distributions. And this predict start model is the one which is like predicting from the network to compute the loss. If we go inside this, there should be a network call. Let's search that out. Yeah, so this is our network call. Here we are passing the some intermediate t state for the edge objects and the object feature and getting some output of that. So as you know, like how diffusion work is, like we first try to add noise to the diffusion model and try to denoise it. So that only it is doing internally, like it is trying to denoise it. Given a t state, we can like predict the x0. So also here we can see given a xt state, we need to predict the x0 state. So that is like what is happening inside this prediction. Going back, so once we have like the prediction of the output, then we are like using the loss function to compute the loss and then finally optimize the weights of our network to finally train the model. So that is the training part of the semantic scene graph. Now coming to the inference part of this model, which is called generate SG. So generate SG is the part where we are actually predicting the output. So let's go through this script quickly. We are loading up the model which we have trained with the checkpoint. Here is the checkpoint that we are loading up which we have trained. This is the model initialization. So they have defined the architecture here inside this class of this model. SG to SC is for basically layout decoder, which we have already trained. So in this script, we are basically generating the script again, which is using combination of all three models, which is the VQVAE, layout decoder, and the semantic scene graph. So we are loading up the checkpoint for the layout decoder here. After that, generate the scene graph and then boxes. Okay. So first we are going to generate a scene graph. Let's see where it is happening. So this is the place where we are generating the scene graph. As we can see, generate sample, we are passing the batch size number of object text embeddings to give out the object edges and the object feature vectors. Once this is done, we are going to pass this information, the predicted information, to layout decoder. We'll quickly see that. So it is doing some pre-processing here, and then comes the layout decoder part. So this is the layout decoder, SG to SC, and we can see we are passing the object edges and the feature vector, which was predicted by the semantic scene graph, to generate box spread. This box spread is basically nothing, the bounding box information, which internally contains the translation, basically the XYZ coordinates, size and angles. And once we have that, we can easily use this information to spawn objects within Blender and generate scene. So that is what it is doing. It is creating a temporary directory, which I've showed you before. Let me quickly show you that again. So this is the temporary directory which it creates, which is used by the Blender to render the scene. To render the scene, they have created their own directory or the different file, Blender py script, which loads up all the objects in the temporary directory and renders a image out of it. Load scene object is the place where inside the it iterates through all the obj file in the temp directory and generate the scene. So yeah, so that was it about like how the model is working and everything. And also in the readme file, they have provided some other information which we can see. In the Python file itself, in the sh file itself, like we can replace the py file to stylize, rearrange, or complete. So even if we have like a partial scene available with us, we can complete that scene using this complete sg py file. So we can also basically use text prompts to complete our incomplete scene. So all those things can be done with the model that they have described. Now they have already released the checkpoint for VQVAE, as you can see here on Hugging Face, but they haven't provided the checkpoint for layout decoder, like while training, and also for the semantic scene graph. And it took me around like a day for doing this for layout decoder and around 4 or 5 days on 8NG or L4 GPU to create this checkpoint for this. But they haven't included this in Hugging Face. So what I did, like I created a pull request on their Hugging Face community to upload those checkpoints with 2K iterations. So you can use this up to train your model. And also the author have updated their readme file to include my name in the news section. Just let me show you that, because I provided them the unofficial checkpoints, which you can also use. So in this you can see unofficial pre-trained parameters for two-stage generative provided by me. We can see this issue where I have provided the links of these checkpoints, which you can also use for the layout decoder and also for the semantic scene graph. So yeah, so that is it about the layout InstructScene paper. Using a text prompt, we can basically able to generate different kind of scenes according to our input. And internally, it is majorly using two components. One is for like generating a scene, semantic scene graph. Other is for layout decoder, which then can be used by tools like Blender or any other tool, maybe like Unity or Unreal, to generate a 3D scene. So yeah, that was about the InstructScene paper. Thanks for watching.